10. In chapter 10, we would like to look at inferences for two population means. In chapters 8 and 9, we looked at confidence intervals and hypothesis tests for one population mean. So in chapter 10, we're going to extend these to two populations now. So our inferences now, just to clarify what we mean by inferences. Remember, inferences are generalizations to the population parameters. So we're going to do it in three forms. The three forms of inferences for us is going to be point estimation, confidence intervals, and hypothesis tests. Now in section 10.1, we're actually going to just do point estimation. We'll do confidence interval and hypothesis tests in the next section, section 10.2. Now, because we have two populations now, so I'm using actually in section 10.1, I'm using the table that's in your book, which gives us a notation for how we're going to note these two populations. So remember the unknown of the population we're looking at here. The first population has its own mean, and that's the unknown for us. Sigma 1, the population standard deviation. That could be unknown or it could be known. We'll look at that later. The second population, mu 2, the mean of the second population. Again, that will be unknown for us. And sigma 2, the standard deviation of the second population. Now, the statistics are x bar 1. This is the first sample mean from the first population. X bar 2 is the second sample mean from the second population. Now each of these samples will have their own standard deviation. So S sub 1 would be the standard deviation from the first sample. S sub 2 would be the standard deviation for the second sample. N sub 1 is the first sample size from the first population we've drawn. N sub 2 would be the second sample size drawn from the second population. Now, here are our assumptions here. Well, it's very important, by the way, I have highlighted here that these two samples are independent samples. In section 10.5, we'll look at the case where we have actually dependent samples or paired samples. So that assumption is very pivotal in this section and the next section. So here's a schematic of what's going on in our work in this section. So here's our first population. Assuming the normality of the first population, remember this is where we're getting our individual sample participants from. Excuse me. And this would be the second population. The random variable is the same variable measured on both populations. So this is the mean of the first population. This is the mean of the second population. Both are assumed to be normally distributed. Or remember, by central limit theorem, each sample size could be at least 30 and our work still applies. Sigma 1 is a standard deviation of this population. Sigma 2 is a standard deviation of the second population. Now what we do is we take repeated sample of size n1 from this population, size n2 from the second population, and remember by central limit theorem, this will be the sampling distribution of x bar 1, and this will be the sampling distribution of x bar 2. This is exactly the extension of what we did in chapter 7, except now we have two populations. Okay, so that's pretty much how these distributions shape up. Now the question might be, okay, we just said the objective is to compare two population means. So how are we going to compare these two population means? Now remember, what we are comparing again is mu1 and mu2. Okay, so that's what we're comparing. Right up here, I'm highlighting it. mu1, mu2. Those are the two things we want to compare. And they are unknown. So how are we going to compare them? What metric are we going to use? Well, the answer to that is, why don't we compare the difference between them? So this way it just builds a theoretical foundation for the mathematical work behind this. So this is one way to compare two population means through the differences between them. So what is the difference going to tell us? Well, this difference between two means is going to be a number, right? Because the average in the first population, average in the second population, these are numbers. So the difference of those will be a number also. Now, just like with any numbers that you think about, the real numbers, the numbers could be 0, positive, or negative, right? So if the difference between the means turns out to be 0, that translates into no difference between them, correct? If difference between two numbers 0 means they're the same, aren't they? Or the difference could be positive, or it could be negative. If the difference is positive, right in here, difference positive, you can move mu2 to the other side, and that would imply that the mean of the first population is greater than the mean of the second population. And if the difference is less than 0, that would imply the mean of the first population is less than the mean of the second population. So that's how the comparison is going to work. Now, the next question might be, well, how are we going to estimate actually? How are we going to estimate mu1 minus mu2? Well, a point estimate of that is going to be x bar 1 minus x bar 2. To look at the difference between the mean of the populations, two populations that is, why don't we look at the difference between the mean of the two sample means? The difference between the two sample means. So here's our point estimate. So this is our first form of inference, the point estimate. Now that we have a point estimate, in order to construct confidence interval and do hypothesis testing, just like we did in chapter 8, we have our point estimate. We need the probability distribution, or as we call it, the sampling distribution of x bar 1 minus x bar 2 before we can do that. Now the other thing, before we actually do those, which we do in the next section, just on its own merit, once we know the probability distribution of x bar 1 minus x bar 2, or sampling distribution of it, then we can actually make probability statements about the random variable x bar 1 minus x bar 2. It's itself, and also we can draw inferences about mu1 minus mu2. So now here's how we arrive at the sampling distribution, or the probability distribution of x bar 1 minus x bar 2. I have it in blue. So if we make the assumption that the random variable, whatever it is that we're measuring, could be age, could be distance, could be, I don't know, the cholesterol levels of male versus female, something like that. So if we assume that the random variable x is normally distributed on each of the two populations, or actually each of those could be at least 30, and we do have independent samples that are drawn from these two populations, then the sampling distribution of mu1 minus mu2 is, well, actually, let me see, we're looking at this, sorry, this is in mu1 minus mu2, this is the same, let me erase that. We're looking at the sampling distribution of x bar 1 minus x bar 2. So the sampling distribution of x bar 1 minus x bar 2, our statistic, is given by central limit theorem to be this. Now, the fact that we have a normal distribution, that's not because of central limit theorem here. The important theory behind this work is, I have it to the right. Because we're looking at linear combination of two normally random variables, or a random variable from two normally populations, it turns out that any linear combination of two normal distributions or probability distribution is also normally distributed. So that's why we have this blue normal distribution. Now, the parameters of this distribution. First, our random variable. The random variable, remember, is x bar 1 minus x bar 2. Okay, that's our point estimate. And its probability distribution is going to be normal. The center of the distribution is mu of that random variable, which is x bar 1 minus x bar 2. And the standard deviation is going to be whatever that is. So we need to find the parameters of this normal distribution, in other words. So what is the center of this distribution? Well, if you work through this, the center of the distribution of the random variable x bar 1 minus x bar 2. Notice here, by the way, this this x bar 1 minus x bar 2 is a subscript. So we're looking at the mean of this. This is a random variable. This is a random variable. A random variable is x bar 1 minus x bar 2. So that's going to equal to the mean of x bar 1 minus the mean of the sampling distribution of x bar 2. So notice here, to the left we have a single random variable, whereas to the right we have two individual random variables, x bar 1, x bar 2. And because of, again, central limit theorem, we know that mu of x bar 1 is the same as mu 1, mu of x bar 2 is the same as mu 2. Okay, so that's going to be the center of this distribution. Now, the standard deviation, actually, anytime we combine two distributions, in this case we combined the first normal distribution to the second normal distribution via subtraction, right? Remember, we do x bar 1 minus x bar 2, that's our subtraction. So the point being, anytime we combine, be it subtract or add random variables, the dispersion or deviations are always additive. So we combine the deviations from the two populations. So that's why we have the variability here under the radical sign. This is the variability from the first population. This is the variability from the second population. And we're looking at, again, random variable x bar 1 plus variability in random variable x bar 2. And the square root of that turns it into standard deviation. And there you go. Now we have the shape of the distribution is normal. The parameters of the distribution, its center and deviation, are known also. They're given by these. So we can actually now, in this section anyways, we can make probability statements about x bar 1 minus x bar 2 and be able to answer those. Hopefully you followed everything that went on here. This is just the theory behind what's coming up. In section 10.2 and beyond, we will actually see more of the formulas. This is just the foundation for the theoretical work that is to follow. Now, so let's take a look at this exercise. In this exercise, we're doing number 11. The question is asking us the following. In part A, identify a variable, identify the populations, determine the null and alternative hypotheses, and classify the hypothesis as two-tail, left tail, or right tail. Remember, depending on the sign on the alternative, true. So just in a way of reminder, two-tail, that's not equal to left tail if it's less than, or right tail when it's greater than. Again, these are the signs in the alternative hypothesis. So the question reads, data on household vehicle miles of travel, or VMT, are compiled annually by the Federal Highway Administration, or the FHA, and are published in that the source. A hypothesis test is to be performed to decide whether a difference exists in last year's mean VMT for households in the Midwest and South. Now notice here what we're doing is, in fact, we are comparing two population means. So here's the keyword mean. And we want to know if there is a difference, between them. Now this is the mean for all households in those two regions. So that's why the difference between the means, that means mu1 and mu2. So it makes it inferential. We're inferring, or we're generalizing to the average in two regions for all households, okay, in those two regions, again, Midwest and South. So in part A, what's the variable here? Well, the variable is vehicle miles of travel, right? And there you go. That's what we are measuring in the two regions. In part B, identify the populations. Well, Again, the population I just mentioned, these are the households in Midwest and South. Those are the two target populations. In part C, determine the null and alternative. The null hypothesis, by the way, in this chapter, always take it to be mu1 minus mu2 equals 0. The null hypothesis, in other words, says there is no difference between the two means. Remember when we first introduced the idea of hypothesis in section 9.1? We mentioned the null hypothesis is the status quo, which means the hypothesis of no change, no difference. And indeed, now you're seeing here. So, if the null says the mean is 0, that means there is no difference, right? Which we can also say it's the same as saying the two means are equal. Means there are no different. Now, the alternative is what the researchers want to know. Is there a difference between the two vehicle miles of travel in the two regions? So it is the alternative that we would like to pursue. So the alternative says, no, there is a difference. We believe there is a difference. Which again, if you move mu2 to the other side, you see an alternate form of the hypotheses. Both of these ways, by the way, folks, both of these, this one and this one are admissible or acceptable in this section and in chapter 10 in general. Now in part T, classify the hypothesis. In part D, well, because the alternative is not equal to, so we have a two-tailed test of hypothesis. And here I wrote down what the mu's are. Mu's are the mean VMT for each of the two regions, right? This is for, again, all households, right? And that wraps up this exercise. Now, let's actually take a look at another exercise where we have to put this distribution, the sampling distribution, to use. Remember, I mentioned once we know the sampling distribution of x bar 1 minus x bar 2, that's our statistic. We will be able to make probability statements about x bar 1 minus x bar 2, just like we do for any random variable, and be able to find those probabilities. So, in exercise number 24, a variable of two population has a mean of 7.9 and a deviation of 5.4 for one population, a mean of 7.1, deviation of 4.6 for the other. The variable is normally distributed on each of the two populations. Okay, perfect. So that means the sampling distribution will be normal, in fact. So in part A, for independent samples of size 3 and 6, respectively determine the mean and deviation of x bar 1 minus x bar 2. Note, by the way, the samples are small, but that's okay because the populations we're told are normally distributed. So when the population is normally distributed, the sample size doesn't matter. But if we were not told that the populations are normally distributed, then we would like to see these samples to each be at least 30. Okay, so let's see. So now we can, okay, it says determine the mean and deviation of x bar 1 minus x bar 2. Now I went ahead and kind of did a sketch of what's going on here. And there you have it. So this is our first population. We were told each population are normally distributed, or each population is normally distributed. So here's random variable x1. The center of the distribution is at 7.9, deviation 5.4, normal. The second population, random variable x2. The mean is 7.1, deviation 4.6. Now, if we take a repeated sample of size 3 from the first population, repeated sample of size 6 from the second population. By central limit theorem, each of these populations, now we're looking at the sampling distribution of x bar 1. Okay, so each of these would be normally distributed excuse me, And the center of the distribution is 7.9 here, same as the mean of the population. The mean of this population will be exactly the same as the mean of the population above. Remember, x1, x2, these two normal distribution, these are the distribution of individuals. So you got, let's say, millions and millions and millions of subjects in here, and quite a few millions, if not more, of subjects in here. And then we take sample from here and sample from there. And these are, you're looking at these two distribution of repeated samples. Again, in chapter 7, we looked at central limit theorem. It's a continuation of that theory. Okay, now what happens is now we combine these two. We're combining these two these two distributions. And the linear combination we're talking about here is x bar 1 minus x bar 2. That's what we call a linear combination. In linear combination, you only use operation addition and subtraction. So here we're using subtraction between random variables. So that's a linear combination. But anyhow, so here we have the sampling distribution of x bar 1 minus x bar 2. It's going to be normal. That's the mean, that's the deviation. We want to find these parameters. So here's how you find the center of this distribution. Mu x bar 1 minus mu x bar 2, and then because each of these, remember up here, see this number, 7.9 is the same as this number. 7.1, same as this number. So right down here we have the same thing. 7.9 minus 7.1, 0.8. So that's the center of this distribution. The standard deviation, I went ahead and plugged into the formula we have up here. That's the formula that's right up here. There you go. This formula in green. That's what I'm plugging into. Okay. And the standard deviation turns out to be 3.64. Okay, so hopefully you follow that. Now, this was all part A. In part B, can you conclude that the variable x bar 1 minus x bar 2 is normally distributed? Explain your answer. Actually, it turns out that yes, we can. And the reason is because the random variable x is normally distributed on each of the two populations. So that's why the answer is yes. In part C of that exercise, determine the percentage of all pairs of independent samples of sizes 4 and 16. Notice, by the way, the author changed the sample sizes from part A. It was 3.6. He changed it to 4.16. So that means we have to recalculate the standard deviation. When you change the sample size, it affects the standard deviation, but the mean isn't going to change, right? It's only that sigma over square root of n. That's in the denominator is just changed. Okay, so we want to determine the percentage of all pairs for those sample sizes from two populations with the property that the difference x bar 1 minus x bar 2 between the sample means is between -3 and 4. Okay, so for part C, I went ahead and put this in a probability statement. Remember, the word percentage for us means probability also. So we want to know, in other words, what's the probability that x bar 1 minus x bar 2, a random variable, is between -3 and 4. That's all we want to know. And there you have it. So I went ahead and wrote it, as you can see down here. So the percentage means probability of all samples x bar 1 minus x bar 2 between -3 and 4. Now remember, he changed the sample sizes on us, so the mean isn't going to change. I got that from part A to be 0.8, but we got to redo our standard deviation, and I redid the standard deviation. The standard deviation is now 2.935. Okay. Now, in order to find this probability, we have a normal distribution, right? So this is what the normal distribution actually looks like for this exercise. The center of the distribution is 0.8, the deviation is 2.935, right? And we want to know what's probability of random variable x bar 1 minus x bar 2 between -3 and 4. So if we want to go to the table in the back of the book, remember that's the standard normal table. That means mean must be 0, deviation must be 1. So I need to standardize the random variable. And that is what I did next. So we have a normal distribution, and the way to standardize it is we're going to subtract the mean of the deviation of the distribution divided by the deviation of the distribution. Excuse me. And I did. So I did the same thing to all 3 parts of this inequality. Subtract the mean by deviation. Subtract the mean by deviation. Subtract the mean by deviation. Now in the middle, what we have is this random variable x bar 1 minus x bar 2 has now transformed into a z-score. The arithmetic of what we did, you use a calculator, you get -1.3, and I rounded this number. It's -1.295, something like that. And the one on the right side turns out to be 1.09 rounded. Again, both of these numbers are rounded to nearest hundreds, because that's how your z-table is in the back of the book, which means when we do this in StatCrunch, our number's going to be off by a little bit. So the answer is going to be 0.8621 minus 0.0968, 7653. It's better than 76% probability. Now, how did I get these numbers, right? 8621, 0968. Let's dig deeper into this. So there you go. I've drawn my distribution. So in order to find, and this is actually a z now. So I went to 1.09. If I look at the table to the left of 1.09, the author, remember, he gives us everything from -infinity up to 1.09. And the part to the left of -1.3 we don't need, because we want area between 2 numbers. So remember, you subtract the smaller area from the larger area. And for these 2 numbers, I actually looked up the table in the back of the book. I'll show you. I have an image from the table here for you. So that's how I got these 2 numbers. So the question again remains, how did I get 8621 for the z of 109, right? Okay, so here's how I got that. This is the z table. I believe it's in appendix page 7, AP7. And I looked at a z of 1.09. Here z went down to 1 and the column 09. Go down the column, go across the row, where the 2 meet is 8621. So that's how I got this 8621 number. How did I get the 0968? Well, I looked up table in appendix, I believe, page 6, AP6. That's where I looked up this number, and I have a portion of that table for you in a moment. And I looked up to the left of -1.3, and that's what I found. And then by subtraction, I got the number. So let's look at -1.3, and there you go. So here is -1.3 right down here. You see that? -1.3. The second decimal in -1.3 is 0. It's like -1.30. So the row column combination right in here, 0968. And that's the area to the left. That is the excess. That's the area we don't need. And that's how I got my 7653 number. Now, how do I do this in StatCrunch? Well, let me first show you what it looks like, and then I'll go to StatCrunch and actually show you how this is done. But looking at the StatCrunch, now remember, StatCrunch, you don't need to standardize, because StatCrunch can handle any mean and deviation, right? So I went to our normal calculator. I put the mean 0.8, deviation 2.935, and of course probability. StatCrunch calls everything x. To them, it's just random variable, but this is actually x bar 1 minus x bar 2. So probability that the random variable is between -3 and 4, and there you go, 76.45 versus 76.53. So we are off by about 8-10 thousandths. That's not bad. The reason we're off again is due to rounding. Up here, when I rounded to 1.3, remember, this number wasn't quite 1.3 and this wasn't quite 1.09. So that's why we're off somewhat. And let's see, and that's about it on this one. So let me go to StatCrunch and I show you how I got this again, just as a refresher. So I'm gonna go up. Hopefully my StatCrunch is still running. 0.8 mean 2.935. Okay, and here you go. You go to Stat. Assuming you can go to StatCrunch. Remember, we go there from multimedia, right? You go to multimedia, and right here is a StatCrunch. You click on StatCrunch here, and this is gonna show up. So I'm gonna go Stat Calculators, and then we're gonna go to Normal. And here's a normal distribution, default 0.1. We're gonna change this default. This was 0.8, correct? So let me actually type in 0.8. Deviation was 2.935. I'll verify these in a moment. And I want in between, so I'm up here. See that? Click on between. Change this to -3. Lower limit, upper limit is 4. And hit compute. And there you go. So I believe I copied those numbers correctly. 2.935. And there you have it. This would be the probability. Okay, so it's exactly the same thing that, almost exactly the same thing that we got. And let me go back to my notebook, and I think with that we are done with this section. So again, hopefully you follow what we did. The takeaway from this section, folks, what we want to take forward with us is actually this right in here. This is what we want to take with us to future section of chapter 10. That would be section 10.2, which we'll be using this in section 10.2. And remember, we have the parameter of the distribution, and the parameter of this distribution are going to be, let's see. Sorry, my page disappeared. Guess I got too much information on it, that's why. Let me show you. And there you go. This is all we're going to take away with us to the next section. Okay? So hopefully you followed everything we talked about. And with that, we are done with this lecture.